Today's show is a special one in our new initiative called BEATS, Broad Education and Technology Series. I'm your presenter, Julia Cosby. I'm presenting a few aspects of quantum research based on our own online research. What is quantum physics? Put simply, it's the physics that explains how everything works, the best description we have of the nature of how particles that make up the matter and the forces with which they interact. Quantum physics underlines how atoms work, and so why chemistry and biology work as they do. You, me, and Gatepost, at some level, at least, we're all dancing to the quantum tune. If you want to explain how electrons move through a computer chip, how photons of light get turned into electrical current in a solar panel or amplify themselves in a laser, or just even how the sun keeps burning, you'll need to know quantum physics. The difficulty, and for physicists, the fun, starts here. To begin with, there's no single quantum theory. There's only quantum mechanics and basic mathematical framework that underpins it all, which is the first developed in 1920 by Niels Bohr, Werner Heisenberg, Erwin Schrödinger, and others. It characterizes simple things such as how to position the momentum of a single particle or group of a few particles changes over time. But to understand how things work in the real world, quantum mechanics must be combined with other elements of physics. Principally, Albert Einstein's special theory of relativity, which explains what happens when things move very fast to create what is known as quantum field theories. 3 different quantum field theories deal with 3 or 4 fundamental forces by which matter interacts. Electromagnetism, which explains how atoms hold together, the strong nuclear force, which explains the stability of the nucleus at the heart of the atom, and the weak nuclear force, which explains why some atoms undergo radioactive decay. Over the past 5 decades or so, these 3 theories have been brought together in a ramshackle coalition known as the Standard Model of Particle Physics. For all the impression that this model is slightly held together as sticky tape, it is the most accurately tested picture of the matter's basic workings that's ever been devised. Its crowning glory came in 2012 when the discovery of the Higgs boson, the particle that gives all other fundamental particles their mass, with existence, which predicted the basics of quantum field theories as far back as 1964. Conventional quantum field theories work well when describing the results of experiments in high-energy particle smashers, such as CERN's Large Hadron Collider, where the Higgs was discovered, which probed matter at its smallest scales. But if you want to understand how things work in many less astronic situations, how electrons move or don't move through solid material, and so make a material a metal, an insulator, or a semiconductor, for example, things get even more complex. The billions upon billions of interactions in these crowded environments require the development of effective field theories that gloss over some of the gory details. The difficulty in constructing such theories is why many important questions in solid-state physics remain unresolved. For instance, why at low temperatures some materials are superconductors that allow current without electrical resistance, and why we can't get this trick to work at room temperatures. But beneath all these practical problems lies a huge quantum mystery. At the basic level, quantum physics predicts very strange things about how matter works that are completely at odds with how things seem to work in the real world. Quantum particles can behave like particles located on a single place, or they can behave like waves, distributed all over the space in several places at once. How they appear seems to depend on how we choose to measure them. And before we measure, they seem to have no definite properties at all, leading us to a fundamental conundrum about the nature of basic reality. This fuzziness leads to apparent paradoxes, such as Schrödinger's cat, in which, thanks to an uncertain quantum process, a cat is left dead and alive at the same time. But that's not at all. Quantum particles also seem to be able to affect each other instantaneously, even when they are far away from each other. This truly bamboozling phenomenon is known as entanglement, or a phrase coined by Einstein, a great critic of quantum theory, spooky action at a distance. Such quantum powers are completely foreign to us, yet are the basics of emerging technologies such as ultra-secure quantum cryptography and ultra-powerful quantum computing. But as to what it all means, no one knows. Some people think we must just accept that quantum physics explains the material world in terms as we find impossible to square with our existence in the larger classical world. Others think there must be some better, more intuitive theory out there that we are yet to discover. In all of this, there are several elephants in the room. For a start, there's the fourth fundamental force of nature that so far quantum theory has been unable to explain. Gravity remains the territory of Einstein's general theory of relativity, a firmly non-quantum theory that doesn't involve particles. Intensive efforts over decades to bring gravity under the quantum umbrella and so explain all of the fundamental physics with one theory of everything have come to nothing. Meanwhile, cosmological measures indicate that over 95% of the universe consists of dark matter and dark energy, stuffs for which we currently have no explanation with the Standard Model, and conundrums such as the experiment of the role of quantum physics in a messy workings of life remain unexplained. The world is at some level quantum, but whether quantum physics is the last word about the world remains an open question. Quantum physics is usually just intimidating from the get-go. It's kind of weird and can seem counterintuitive, even for the physicists who deal with it every day. But it's not incomprehensible. If you're reading something about quantum physics, there's really only 6 concepts about it that you should keep in mind. Do that and you'll find quantum physics a lot easier to understand. There's a lot of places to start this sort of discussion, and this is as good as any. Everything in the universe has both particle and wave nature. There's a line in Greg Beer's fantasy duology where the character describing the basics of magic says, "All is waves with nothing waving, over no distance at all." I've always really liked this as a poetic description of quantum physics. Deep down, everything in the universe has a wave nature. Of course, everything in the universe also has a particle nature. This seems completely crazy, but is an experimental fact worked out by a surprisingly familiar process. Of course, describing real objects as both particles and waves is necessarily somewhat imprecise. Properly speaking, the objects described by quantum physics are neither particles nor waves, but a third category that shares some properties of waves, a characteristic frequency and wavelength, some spread over space, and some properties of particles. They're generally countable and can be localized to some degree. This leads to some lively debate within the physics education community about whether it's really appropriate to talk about light as a particle in intro physics courses. Not because there's any controversy about whether the light has some particle nature, but because calling photons particles rather than excitations of a quantum field might lead to some student misconceptions. I tend not to agree with this because many of the same concerns could be raised about calling electrons particles, but it makes for a reliable source of blog conversations. Thank you for watching Beat's special introductory presentation on quantum physics.